Hello there, welcome back, guys. Hey, this is Dr. Mandis talking to all my wonderful students. Look, I just want to talk briefly and quickly just about concentration. Concentration involves calculations, but they're not novel calculations. They're just unit conversions yet again. But concentration, man, seriously, it is just the idea of how much per how much. That sounds dumb, but it's how much per how much. How much solute per some amount of solvent. The way that all these concentration units differ, you got molarity, molality, you got normality, you got parts per million, parts per billion, percent mass, percent volume, percent mass volume, whatever the heck it is, man. It is just some amount of solute per some amount of solvent. In chemistry, most of the times we don't care about mass of things, we care about the number of particles. So that's why so often you see the mole of things. All right, the mole of that solute. Okay. The solvent, on the other hand, usually it's molarity. 9 times out of 10, what you're dealing with is molarity. Sometimes normality, but not in the general chem course, but molarity. All right, because you have a certain amount of solution that you're going to measure in the lab. How are you going to measure that solution? You're going to measure it by volume, and so that's liters. Cool? But for the most part, you're working in the lab, same temperatures and all that, but volume can change with temperature. Things expand, contract with temperature. So volume isn't a constant. For the If it matters, like with when you're doing freezing point, depression, boiling point elevation, things like that, you're looking at temperature changes, so your volume's not a constant. So that's why we have molality. Molality is moles per kilogram. Okay, other than the volume versus mass difference, because mass is a constant, it's not going to change with temp. The difference is this is the volume of the whole solution. Why? Because you're dealing with the solution. You're pouring something into a beaker, into a volumetric flask. You're pipetting the solution. How much of the solution do you need? That's why it's the volume of the entire solution. For molality, you're just dealing with the mass of the solvent. Okay? That's where you can get confused. But if you understand why we're doing it, it makes sense. I thought I would just give you a couple quick examples. One is right here, number one. I put, 32 grams of ethylene glycol into a certain mass of water to a final volume of yay. Okay. So if I ask you for the molarity and the molality of the solution, you need molarity. Well, then you need the mass, the mass of the water, your mass of your ethylene glycol, and your final volume. If you're looking at molality, then you're still dealing with your solute, and instead of the final volume, the water. For both of these, you're given a mass of something because that's what you would measure out in the lab, but you need to convert mass to moles. I wrote that right here for you. Remember, when you do a conversion, you need to convert units. So basically, grams of solute cancels out the grams of solute, in this case ethylene glycol, leaving you with moles. So you can readily convert to moles. Totally Most of my students, especially the good ones, the smart ones, won't write out the units, and then they often tend to do 32 times 62 or something like that, make mistakes because you're too good to write it out. A little bit of sarcasm there, guys, because it's really common. After decades of teaching, I've seen it way too many times. But anyway, let's talk about the molarity. For the molarity, you're going to take the moles and divide by the total volume. Okay, that's the main thing. It's the total volume. For molality, take those moles and divide by the kilograms of solvent. Usually that's a conversion, grams to kilograms. If you have issues with conversions, kilo means thousands. So 1.46 grams is how many thousands of grams? It would be 0.146 thousand grams. Okay, like 146,000 is 0.146 million. Okay, anywho, let's move along here. The only other way sometimes you have to deal with molarity, especially in the lab, okay, is when you have a solution and then you add water to it and dilute it. So in part B, I said what would be the molarity if 300 mils of water was added. You could fall back all the way back to the beginning here and go, hey, I have the moles of solute. Let me divide by the new volume of solvent. And that's exactly what you should do. And you get your new molarity of 1.03 moles per liter. Some students like things they can memorize that are a little bit easier to get to. And that's okay. If that's your gig, that's your gig. M1V1 equals M2V2. You have an initial molarity and initial volume of that, and you're trying to find the new molarity at the new volume. So you're solving for the second molarity right there. Plug your numbers in and go. If you look at this, okay, the advantage is that you don't have to switch the liters. It's 200 mLs divided by 500 mLs, and that will cancel, and that's fine, and Dandy leaves with molarity. But let's just back up a second really fast and say, hey, 2.58 molar divided by, or I should say multiplied by the 200 mLs. If you just do that, you know what that gives you? That's moles per liter times liters, so to speak. That gives you your moles. Okay, that is basically how we got this number, if you think about it. And then you divide by the new volume. So then you divide by the new volume. So it really doesn't matter where you're going to go. You're going to get the same number. The question is, how do you like to do it? Get the number of moles, divide by the new volume, or have something that you can memorize, M1V1 equals M2V2, and plug and chug. Choice is up to you. Nobody will ever know how you did it. Okay, the only other place molarity really comes up, see how we're back to molarity, not a whole lot of molality. Molality is pretty much only with colligative properties. Molarity of a solution is when things dissociate in solution. Sodium chloride dissociates, strontium chloride dissociates, aluminum chloride dissociates. These dissociations occur because they are ionic compounds dissolving in water and they're not staying together. In that case, your concentration is going to change. So what I gave you was equal concentrations, okay, with a differing number of chlorides. This is 1 chloride, 2 chloride, 3 chloride. And students often can't figure out why the concentrations change until you really just write it out. If you look at the equation, sorry, brain fart there. If you look at the equation and then do a mole-to-mole ratio, you can see why they change. Because the molarity gives you moles of the solute, NaCl, convert that to chloride. For the strontium chloride, you get 2 chlorides, so your mole ratio is 2 to 1, so it would double. For the aluminum chloride, I didn't bother to write it. Your mole ratio is 1 to 3, so you're going to triple it. And that's why sometimes you look and you say, hey, the numbers are the same. And then all of a sudden, hey, it doubles, it triples. And the basis for all of that is hidden in those dissociation equations. So know your dissociation equations, have an idea of the underlying theory, and then numbers make sense to you. That's all for today. Hopefully you'll have a good old time with that. Thank you.